let's introduce a concept of a field. A field is basically a set that is closed under addition, subtraction, multiplication, and division, but except dividing by 0. So it is actually, informally, it's a very advanced set. Let's take a look at some well-known examples. Firstly, we are familiar with the natural numbers, and the set of them is denoted by n. And then we can have the set of integers denoted by z, and we have the set of rational numbers denoted by q, and then we have the set of real numbers denoted by r. So which of these are fields is the question. So let's take a look at the first example. N is just the set 1, 2, 3, and so on. And this set is closed under addition because if you add any two numbers, you get another natural number. But it is not closed under subtraction. For example, 1 minus 3 is not inside the set. So N is not a field. Let's look at Z. Z is basically the set of integers including the negative integers, 0, and the positive integers. And this set is obviously closed under addition and subtraction. It's also closed under multiplication, but it is not closed under division. For example, 1 divided by 2 is not inside this set. So this is almost a field, it just it's not closed under division. So it's not a field, but it's very close to being one. And for sets like these, there's actually another name for it, it's called a ring. Basically a set that is closed under addition, subtraction, and multiplication, except division. Let's look at Q, the set of rational numbers. This is basically defined as the set of all P over Q such that P and Q are integers and Q is not 0. And this is obviously a field. Why? When we have two rational numbers and we add them up, we get another rational number. And if we subtract, we also get another rational number. And for multiplication, it is closed as well because we get a rational number, AC over BD. And if we divide, that's equal to AD over BC. So Q is a field. And for similar reasons, R is also a field, which you can check. However, I want to generate a field. I want to generate a field between Q and R. Let's see if that's possible. So to generate a field between Q and R, let's find something that is in R but not in Q. For example, square root 2 is not in Q. So what is square root 2? Square root 2 is a number which if you square it, you get 2. And, oops, sorry, it's not in Q. So what if we forcefully insert square root 2 into Q? So we get Q union square root 2. But this set is not a field because you can have numbers like 1 plus square root 2, which is not inside this set anymore. You can have numbers like square root 2 over 8, which is not in the set anymore. However, after we insert square root 2 and we have so many numbers that are not inside this new set anymore, let's just add them all into the set. Alright, like if square root 2 over 8 is not inside the set, let's just add it into the set. And if 1 plus square root 2 is not in the set, let's just add it in. So in the end, we get to generate a field in the form a plus b square root 2, such that a and b are rational numbers. And this is a field. Let's verify. If we have two such numbers, and we add them up, we can have another number in the same form. And similar logic goes to subtraction. For multiplication, it's a bit complicated, but it's still doable. If you expand this, you'll get something like AC plus 2BD plus AD plus BC square root 2. And for division, we can multiply both sides by the conjugate of the denominator. So this becomes c squared minus 2d squared. And if we expand this all out, we can get AC minus 2BD over c squared minus 2d squared plus a BC minus AD over c squared minus 2d squared square root 2. And this is also in the form a plus b squared root 2. So indeed, this is closed under addition, multiplication, subtraction, and division. So it's a field. And it is strictly between Q and R. And we have a name for this. This is the set Q with the square brackets square root 2. Basically means we have the field Q, we join the root of 2 into this set, and we generate a field. So for the same way, we can consider R and we want to extend this field into a larger field. So firstly, we need to find an element that isn't in R. And we can define one. We let I be the solution to the polynomial x squared plus 1 equals 0. And for the same logic, we will generate a field Ri, which is in the form of a plus bi, where a and b are real numbers. And it's a great exercise to check yourself that this is a field as well. So now we have this new field that we have constructed, and because of its nice properties, it is very famous. We use another symbol to represent this. We can say this is denoted by C. And all numbers in this form are called complex numbers. And let's get back to our intermediate field Q square bracket square root 2 R. And of course, this is not the only field in between those two fields Q and R. There are also other fields like Q square root 3 or even Q square root 2 and 3, which is actually q square root 2 as a new field, and we adjoin square root 3 into it. So these ideas and concepts about fields is quite important in mathematics. There is a whole field of mathematics describing these objects. It's called field theory. And there are also a lot of amazing fields that we haven't talked about. For example, all of the fields that we've talked about are infinite. There are infinite elements inside, but there are fields which are finite. They have a finite number of elements inside. So this is field theory and how we can use it to construct the complex numbers.